I do have to get this right. Seems like a miracle. Okay. Yes. So this is POX. It was box once. It used to be Basics of Complex Systems when I started. Now I changed it to Principles, which is POX, and we do talk about pandemics, so that's good. Not just because we had one and are sort of in one, but because we've been talking about that since 2002 or 3 when we did work on that sort of stuff. So that's part of the course, for example. But so POX is a nice name. So you guys are POXologists. There is going to be the names haven't changed yet, right? So it's a bit odd, but I call this POX Volume 1, Volume 2. There's Volume 3D, which is a independent study thing that's going on now, and it's for people who have been through the 2 courses. So this structurally is a 1-year thing. You get to escape at any point, actually, because that's because of Stanley Milgram, right? You can escape whenever you want. But especially, I guess, at the mid-season finale, right? So you can do that. So I was going to just sort of point to a few things. There is a website, and there's a whole cascading sort of series of these things, palimpsest style, right? So you can find yourself possibly in the wrong one. But you know the year, right? So this should be at the front. That should be kind of on everything you come across. You might be, if you use Google or some other fun thing like DuckDuckGo, you might find things from the past. So this is the main site, right? And it is linked to on everything, and I have it sitting in Teams, which is a fun thing that Microsoft made and sort of works, but see, I can't find it now. Where is it? No, where is Teams? Evil thing. Anyway, Teams exists. The Teams thing exists. I switched it on. It will get populated a little bit. It has become the place where here you go. We'll talk about things. So, for example, just to put things inside of other things, the course website is inside Teams, right? But the main thing, we'll have some other channels. I'll add some pieces here. But so if you even just go to Teams, you can escape to the right thing. And it'll be structured like this. There's a big button that glows when you go near it, right? So that's usually you don't want to push those ones, but in this case you do. And I'll try to keep this current. These are the current instructions. There's a little bit of stuff at the front here, right? So it's stories of the POX. It could be stories of complex systems, actually. But I'll show you a little bit around. But basically, you can always come back to this and this will give you a little summary. There's sort of an assignment each week, including this week. Just 2 questions, just to give you a little sense of things. Also an opportunity to say no thank you. But I promise you this is, great. And there's a lot in this course. It's the everything course. So due dates are on Fridays. We'll figure out office hours, which, unless there's great calling for it, we'll probably do over Teams. I think it's more egalitarian, and I can do the righty thing. You can be wherever you want to be, which is probably good. But we can talk about that. Blackboard is also something that exists, but we've resisted anyway. So that's for grades, and that's what we'll have running there. It is a black box to me. Okay. And we have an assistant. So I'm the deliberator. We have an assistant to the regional deliberator, Dylan Casey, who has been processed through this as well. And right, you're finishing a PhD in complex systems and data science. Yeah.
I went through both versions of this class, 1 and 2, and I'm a doctoral candidate in complex systems and data science.
Right, which I'll talk a little bit more about. Some of you, of course, are in it, but I just want to give a little history. It's quick. So awesome. All right, so there'll be adaptations. The theme will be the disk world, so you don't need to worry about that, but usually I theme things in some way. So that'll just be quotes from the disk world, Terry Pratchett. Again, you don't need to know it. I might try to put videos of slow TV, therapeutic stuff. Okay, so this, if you come, again, this is my own site. If you come to teaching within it, there's just a giant thing that gets you into the right place. These are previous versions of it. And just to show you some of the things that happens eventually, like stories, this will be we eventually kind of just have this kind of history of everything that's happened, including these videos, which probably may or may not work. This is an older one, so this is assignments. Maybe this one. See, I'm lost already. Yeah. So there'll be archives of the lectures themselves, right? So that's what I'm attempting to deliver here before I melt into the floor. So they're all on YouTube. I'll try to annotate them properly. That takes a lot of work. There are episodes that I developed over a long period of time. So you can see there are 400, close to 500 clips here, which is kind of maniacal. This is a bit of a dangerous place to go into because there's a lot, but that's basically everything. The place that you can have some more fun navigating is the slide sets. And so that's here, right? So, so overview, I'll touch on these three a bit today, depending on how we go. And so once you jump into one of those, so there are a lot. This is the full, like I said, a full year's worth of stuff. Plus, there's actually 2 years. So we don't get into everything. This is sort of the stopping point, is complexification here. Okay, so if you go to one of these, you would find clips. Like there's a whole episode. It's from a previous time, and then little clips of things which are there. Okay. So, but again, the stories thing will be kind of a journal for the course where I put everything. Oh, okay, it's not bad. So there's a course. As I said, you can find it here if you want to bookmark it or however you do that sort of thing. Bookmark, hilarious. Put on TikTok. I don't know how you do these things anymore. So, but it's basically, it's on Silk. I don't know if you can see that, but it's teaching courses, my thing, teaching courses, then just the full year, and then PoCSverse. It's the PoCSverse. There are weird things in here, and you can just ignore as much as you want, right? So if you've seen Severance on Apple TV, that is a very enjoyable little shout out to that, which macro data refinement, I'm like, that's what we do, that's good. So our work is mysterious and important. All right. Okay, not dead yet. I was going to plow through a little bit of this, just give you a sense of how things work. Right. Interesting. Yeah. So let me see if this still functions. Good. Ah, excellent. It's adaptable, right? You can change depending on the instrument you need. But I prefer sporks. Okay. Oh yeah, I should tell you this. So when you well, these people are older now. One of them is in college, and the other one's going to college next year. But these are important creatures relevant to them. This is our third creature in the house, which is Pratchett the cat, named after Terry Pratchett. So again, if you've never heard of that, just ignore. But he has a little Instagram going on where we just document the life of being a cat, which is pretty good actually, if he's our cat. Okay. Yeah, things are pretty bad here. This is the world we live in. With the spork, excellent. Titanium spork, really good. Okay, so let's see if we can make some sense. Yeah, so he's on Instagram and just doing his thing. I had to step over him to make my way to the up the hill today. All right. Okay, some course information. Are you going to work? Oh no. Oh, because it's this. Wow. Oh, my spork is dead. All right. Okay. Dead spork. So all of this falls underneath the Vermont Complex System Center, which is what we call ourselves. It's there's a lot of rogue behavior going on here, according to whoever you talk to for us. It's what I want to get over to you is like, this is basic modern science, right? just trying to do the right thing, because it's a renaissance time in science. I think that's true, because of the the revolution in instruments and measurement and the data we're getting. Right? And so that's happened in different stages, in different fields. The physicists were running around with too much data and they had to throw most of it away a while ago. Astronomy is only about 2000. I'll sort of talk about this again, right? Before that, it's like you go and look in a telescope, you write your thesis about it, you get a paper. If it's cloudy, you're in trouble. Now, of course, we're in a very different world. We've got the James Webb thing, for example, but arrays of telescopes that image the night sky, and it's just a different game. You need different skill sets. You can ask the same questions. They're all still there, but you find yourself asking more questions because you've measured more things. And you don't, like I said, you don't have to be in Twitter, but if you go to the instructions page, there's a little thing lurking on the side, which is the tweets from PoCSverse, the voice of and just to sort of go on with that a little bit, this is from Freeman Dyson, who did say some very good things. But this is, if you've read Kuhn's book, which was a big deal when I was younger, The Structure of Scientific Revolution, was this idea that we just throw everything out, or we really, we come along and have new big ideas, and it's often it's theories. That's sort of the framing. Like Einstein appears, Annus Mirabilis, which we'll talk about again, but it's like 5 papers in 1905. Las Vegas was also started in 1905. So anyway, there'd be these revolutions where everything's thrown out before, and it's not really true, because eventually with science we figured out core things, right? Newton's law of mechanics operates very well, very well. And then the limits, it falls apart, and now we tend to understand that. But it's a long game. Anyway, so this is just this sort of thing, pointing though to building tools and instruments, right? And that's more and more, in the last 20 years, that's emerged I think the right thing to do, the sort of reasonable way to kind of approach science now. It's a big mess. It's hard to look at these things. You have giant networks of whatever it is, people, things connected, whatever it is, massive amounts of text about everything, of course, unbelievable amounts of video, and then just measurements from, say, satellites or whatever of Earth sciences, all those things. So you get to ask the questions you had before, but you start to see new questions because you looked. And just like you would in grade 4, if you look at the list of how science works, the first thing is to look at some stuff, right? We got a little carried away. It's like, no, you have to have a hypothesis, which apparently you think of in a box somewhere because you understand all of humanity and your Marx or something, right? But anyway, and your mother makes your food for you. So looking at things is good. So we do a lot of looking at things and turning them over and seeing what's going on. And these are our things: describe, explain. That's basic science, the first 2 parts, and then you get to do create and share. And it's sort of a serious play thing. Lots of things. We've got lots of funding over the years. It's changed a lot. We now have funding from large corporations, which could be evil, but Google said it wasn't. Don't be evil, but it could be, evil's just, it could be, right, like super evil, right? They dropped that, I think. So we've lots of press coverage for all sorts of things we've done, from, creating the xenobots, the Bongard stuff, which will, obviously kill us all, these little tofu things one day, measuring happiness to see how it goes down as the xenobots take over. There are lots and lots of things in this complex systems thing. So, and the educational platform is complex systems and data science, which I'll talk about in a second. We've had our own winter workshops for students, which are all asleep maybe for a while, right? Yeah, but it was fantastic. What's that? Maybe. Okay, Juniper Rainbow, just incredible. It's a magical place if you haven't been there. We've hired complex systems people, where you put out a really general, open invitation for people to apply. We've had things where there's everyone from, like ethnologists to physicists applying for one position, and then they sort out where they'll end up. So that's been good. Of course, academia is actually it's incredibly liberal, right? I mean, sort of famously very left-wing if we talk about politics, but in their work, they are super conservative. They're ultra-orthodox, and it took me a long time for the word conservative to get in my brain. And I'm like, oh, okay. So it's a struggle. It's okay. It's sort of part of the tension, I suppose. But it's taken a long time for people to flip into like, oh, systems kind of matter. They've always mattered. We can now also measure them in ways imperfectly, of course, imperfectly, but and that's a bit of a trick for us. We can measure massive amounts of data, but it still might be, a bazillionth of what you really need to measure. But that's a tricky thing. NSF Career Awards, that really changed. I think in the time I've been here, lots of those. We got a P case, and Josh Bongard, because he is of median height, ended up standing next to Barack Obama when they took the pictures, because they ordered everyone from tallest to shortest. So there's some merit in that. We have a couple of things for graduate students that I want to always keep going. The Scraps, which is the Students Complexity Research and Pizza Seminar, right? So we know what's going on. When I did my PhD, we didn't have one, and I created one, and it was SPAMS, the Simple Persons Applied Math Seminar. So we had to really work. The Russians were the worst. The Russians were absolutely the worst. You had to make sure. So I had to have a decree like, you have to come to the talk because one of your, no one gets food. The food was afterwards. Yeah. So really had to crack down on them. Very untrustworthy. Anyway, so that was fun. What's that? Food afterwards was the thing. Let's see if spam still exists. Yes. I made this page. Awesome. I think therefore I spam. I don't know if the spamometer is still there. No. The spamometer was this thing I labeled over to how many units of spam. It's how many talks you gave. I think Leo Pachter, who's now a professor of math at Caltech now, he might have had the #1 position there. Yeah. Anyway, we want you guys to have fun with that, and there's usually someone who's in charge. Yes, I thought so. Right. Okay, good. So if you want to be involved with that, what's the best way to?
I'll send a message on the Slack.
Okay, good.
Today, after class.
And I think I'll have it again, but there is a Slack for graduate students in complex systems, which it's the best way to find that. Do we have that on our website?
No, I just add people as their
okay, there's a mysterious mechanism called Juniper. But if you want to be, you could maybe write on our Teams thing, be part of that. So that's a community. We're also trying to go to the food truck thing every Friday because it's going through September. It got rained out last week, and it's this week, but not the next week. Anyway, there's music. The truck stop, which is down over there near Speaking Volumes and off Pine Street. 6 p.m. on Fridays. You should go. You eat food. Talk to other people. We have the Talk Octopus, which we'd had a seminar for a long time, but we started that in the pandemic. And so it's great. It's online, right? Zoom, one of these things. Everyone's been doing it now. I didn't quite say the words, right? This is our mascot is a Roboctopus, and it just is. It's an octopus in a robot suit because they're interesting things. And also we didn't want Bongard to keep us on the do not kill list anyway. So, okay, we have lots of mascots, so lots of fun things, tardigrade, so we're really hoping that relationship stays, right? That's the thing. The excellent tardigrade. We have sea otters, which is just because they're great. Yeah, right. And now we have, where are they? Oh, I might have lost them. But we have a lemur, ring-tailed lemur. So we're running an experiment, which is there an online page for that? Is there? No. It's only for undergraduate, the first years so far. We might open it up. But basically, it's this Oura ring thing, which measures, the measurement thing, right? Measures everything, everything it can, but heart rate and all that sort of stuff. And it's really focused more on sleep and health, right? Rather than you becoming the most awesome, which is Whoop. And so it's a bit like Apple. Apple's trying to do the health thing. Anyway, lots of data. We only need a small sample of blood once a semester. It's nothing to do with the experiment, but anyway, so but we just thought it'd be fun. Mass Mutual, yeah. Anyway, that's good. We got $2 million for that for this year. It's a big thing. We got I mean, these are huge. $5 million for Mass Mutual is the biggest gift by any corporation to UVM. Google, $1 million. So these have been great. So we're interested in many things. Just a giant list, right? So there are systems everywhere. You don't need to remember these. I did want to sort of just say the history of this. There was a data science undergrad. That's really held between math and stats, and because of the tribal nature of everyone, math, stats, and computer science. So there's it's not working. It totally exists, and it's a great thing. But the admin part is trying to figure themselves out. Do we need a department of data science, of dark data science, which would be DUDS? So clearly, we can get that in. So it's a squirrel. But we run the graduate one. That's our thing. Platypus, strange and adorable. That's the certificate. So that's 5 courses. Some of you might be in that now. We've had that. That was the original thing we set up. Then we went to a master's and then a PhD. And none of these things we thought about way, way back, right? Like this was just sort of an organic growth of like, oh yes, we should do this. This is the conservative thing is, oh, you should just get a PhD in math or physics or sociology or whatever, just the standard thing so people know who you are. Okay, I know. But we got a little excited. So these are the core courses. This one, which you can take whenever you want, but there's data science, which has a couple of instructors now. It's spread out, it's very big, it can only grow. Laurent teaches modeling complex systems, or MOX. So why is it called complex systems and data science? So it's area of study plus what we're using to do it in a rough way, right? Just in a bit of a fun way. Stars and telescopes it's astronomy, right? So there's a little quiz. Rocks and hammers. Yeah, all right. Yeah, fluid mechanics, right? Yeah. Started my PhD. The person I was going to work with wasn't there. I went much later, but they'd been shipped off to another place, and because they like teaching, basically. But I got set up with someone who was a fluid mechanics guy, and that's a good conservative place. That's like real, and if you don't do it, there's something wrong with you. I remember I said I was interested in language, and it's like, fluids. Yeah, anyway. Fluid dynamics. Brains and giant imaging machines. Or mice, maybe. Mice brains and very small imaging machines. That's the neuroscience maniacs. People in deception, essentially. Basically, psychology. We would do anything with a psychologist like, so there's no deception in this experiment. Can we at least draw some blood? Mind you, the deception is actually in the field itself because it's a disaster, right? I mean, and no one gets away with this, right? Physics was a maniacal place for thousands of years and still is, dark matter. Right? Okay, guys. I come from physics, so I'm done. But it's a huge mess. It doesn't seem like many of the famous things about, the Stanford prison experiment, the marshmallow test, all of these things that supposedly, govern your future existence beautifully and work fantastically can't be reproduced because if you use cookies instead of bundt cake, it doesn't work, anyway. So it's a big problem. There's a lot of arguing in that field about what to do next because the reproducibility crisis. I just want to say it's not. There are a few of us around who really I escaped from manufacturing. Who really feel this is not a great naming, right? Like whenever you say that our team is the pure one and then there are others, we're not in a good place. So I think it's pretty much embedded. And of course, then also when you have like posters of genealogical trees on the wall that go back to Euler, it's like vampires with bad dress sense situation. So that's no one's going to get off, right? The science is hard, and we make terrible mistakes, and we should be able to, mind to mind. So we'll call that second fifth. Okay, and then complex systems and data science, right? That's what we're doing. That's the thing. So it's a system science. There have been various versions of this over time. Data science wasn't really a framing until we, maybe 12 years ago, and it's exploded. Statisticians are dismayed, although within their ranks, 80s even, and the 90s, there were people saying, maybe we should call this data science. Like there's sort of a history of people popping up and saying, why don't we call it data science? I'm like, no. So, but it is bigger than statistics. It's visualization. The code size is enormous, right? So, if you built statistics, there's a lot of things would have been very different if we had computational stuff, right? I mean, obviously there were aliens thousands of years ago and they built some pyramids or whatever, but they didn't give us a computer. If they'd given us computers, then maybe we don't understand the pyramids. Maybe they are. But if they'd given them, we understood them, then we would have developed a lot of sciences differently. And they'd be problematic in other ways, but there's an enormous amount of pencil and paper stuff that is pretty fantastic, but maybe, it's not going to do everything you want. This is our group, Computational Story Lab. I work with Chris Danforth. Some of you are in that group. There are story labbers. We're always interested in people. This is some of them. They are off doing very interesting things. Because the pandemic, some of them moved back, which is great. Yeah, they'll want to move back, which makes sense. If you want to read, it's now a couple of years old, but if you want to read a thing about me and Danforth, this is a nice thing. Like I said, we've had a lot of press, but this was a nice interview thing that's good. We measure happiness, but we really measure meaning and we really do other things. So, all right. Okay. Yeah. This is not complete. This is a sense of what I've done in my existence. This is networks way back when, right? So networks became the giant thing, and I'll sort of put them in a spot later on, but this is river networks. This is continental scale. That's the Mississippi, for example. And so I did a lot of work on that. There's a lot of stuff in scaling, which we'll talk about. A lot of stuff on, this is all social contagion and biological contagion. So this is a long time ago, but one of the things, if you really get this into your head, is that you will understand but not be able to change necessarily the world, right? So the COVID-19 made plenty of sense, unfortunately. And we actually did some good things with the state, but there are limits to what you can do. Anyway, this moves more into stories and language. So, but I'm kind of interested in everything. All right. Okay, so of course here, this is basic stuff. It's here. There is a syllabus. You can find it up under things. There are things. There are even things where students said nice comments, selected obviously, so you can see if other people liked it. I look at that to make myself feel better. So office hours we'll sort out, right? Yeah, and we may have some like bonus ones or whatever. Yeah. There are a lot of slides here, and let's just look at them a little bit. So there's let's just go to one. What am I doing? They come in 3 types. So if you're on this page, you probably don't want this one. You can see that they're beasts of things, and I do apologize. I've tried to optimize them, but it will have when it was updated. These are the slides that I'll serve in lectures. Hopefully they won't explode too much. Adobe is whatever. These are little freeze-dried snack slides. These are the fresh ones. These are freeze-dried snacks. So that's like 9 per page. So that's like a little flat thing. And look at that. Oh, so slow. But none of the links will work in this. This is, if you really hate trees, you could print it out. But it's also an easy overall summary thing. And then these ones are with all the little reveals flattened, right? So this is maybe what you want to look at. Okay. And they're on toast. So fresh, freeze-dried, and on toast. Yeah, totally makes sense. All right, so that's the pack and go. That's how they're structured. I used to have little navigation things, but if you go around and like do this, you can, depending on your, like for example, that didn't work. Wow, that's amazing. Yeah, does it work here? There you go. Just. All right, didn't work. Okay, so I thought you could navigate. I guess not. All right, so that's gone away. There are web links. They look like this, right? So it's connected to the world. And this is supposed to be like, rather than a book, right? This is supposed to be this online thing that I've been building for a long, long time. So if you have, there are references back here, so you can go to them, and it will go to a PDF, which some large publishing company wants me not to have online, right? And occasionally I get funny little emails, but it's just a cache of things that I've manually downloaded over the time. Never use Sci-Hub. Never use Sci-Hub. Don't use Sci-Hub. Or Tor, or books. Never use those things. It's wrong. Okay. I mean, burn it all down. It is an absolute disaster, this publishing thing. We do all the stuff for free, and it makes no sense. And Nature, for example, now, you have to, I think it's $11,000 for some of the publications for them to be open source. For your 3-page thing that was destroyed by reviewers to be open source forever or something. $11,000, that's something that's gone wrong. I mean, we could say that about a lot of things, but that's very sort of clear. I'll link them to Amazon, but you shouldn't. You can buy them from wherever. Just to say that there are horrors inside. It's ZLaTeX, Beamer, Perl, Perltech, Emacs. Yes. You don't have to do any of those things. I'm going to try to set things up, the assignments on Emacs. Look at the joy of Emacs. So great. I'm going to try to set things up on Overleaf for you for assignments. So that's a distinction. If you're a graduate student, I want you to do the assignments in LaTeX. And we can talk about, we can kind of work through that. And okay. And otherwise, you don't have to do that. There you go. Fun things. Great. So season 18. I said they were going to have the stories, which is better than calling it streams of consciousness. It's all connected. I'm really, quite a serious person. Okay, and I've showed you these things. Hopefully these things are being recorded. Yes. They're bottle episodes, so you are stuck in this box. You got to escape for a couple of years. We all did. Maybe some tropes. And I will say that NSF supported this. I managed to get a career grant. It was actually in the social and economic sciences. It was never mentioned in my department at all. They just did not. It was not acknowledged in any way. It was obviously wrong. So, but it was very helpful, and all the work we've done on happiness, which is in PoCS Volume 2, kind of comes out of that. One of the big things in there I never quite finished was play. The play project was about how people play, and it's gone into various ways. So for socio-technical computation, I think that's right. Like people plus computers. You see it every time you do a capture thing. Where are the sidewalks? Where are the bad guys? Like those things are pretty sinister. And I know that it's for mapping, but well, yeah. But that's it's people plus computers, and so playing crunch was one of the things. But part of the career grant is to build courses, and that's where we are. And I'm excited to have a volume 3D thing. Okay. So we got Slack. You should be Teams. Slack is going to come along as well. This is not quite right, but the idea is there are assignments. And I want to have projects where you give a talk at some point, which is going to be recorded. We'll share that online somehow in Microsoft, which variably explodes. And then at the end. Grading works like this, 3, 2, 0, 1. 1, 0. I went back up. And this has worked well for a long time in a lot of spaces. It means that little blocks they're more like ABC, right? So it's easier for anyone for the grader and for the gradee to comprehend. Okay, basic things. This is, I'll point to a few books before I go on and get to scaling. This is an old friend of mine so I'm from Australia. This is, we went to university together. So, outside the US, you go straight into degrees, right? So you have high school kids. Next year, they're in the cadavers in medical school, right? So 7 years later, they're a doctor. He's a brain surgeon now. I would trust him, I think, although I know him in ways that worry me. He said that brain surgery is like the greatest video game you could ever play. So maybe. But he handed me this book and he said, because because we were talking about chaos. James Glick's book was very famous. Glick? Glick? It was very famous at the time. It's very inspirational, and like a lot of these things, like Carl Sagan inspired a whole generation of people. Of course, other scientists were upset about that. But, right? So there are markers, and for me, it was this book. It was writing about the Santa Fe Institute early on, so things were still kind of developing. But the Santa Fe Institute was established 1980, 84? Okay, the grooviest decade. No, that's the 70s. The most excellent decade is the 80s, the fluoro decade. The last quiet decade. You watch Stranger Things, right? It's the last, and I mean that in the sense like the connection, the internet, the web starts in 92, and suddenly it's like, okay, so Marikov, handed me this book and said, no, chaos is done. You should read this. So that dictated, a lot of future for me. Kind of a nice thing that I can say now is I'm, what am I? External professor at the Santa Fe Institute. So that's finally, it's a nice thing. It's possible that I wrote papers that said that some important people there made mistakes about things. So that probably put me in the black sheep box for a long time. But anyway, I'm part of it, and it's very exciting. So that's a place you can visit for the summer school is a thing to think about if you're a PhD student. Pretty cool. All right. I went there in maybe 96, I think, yeah. So these are just some others. There's another great Glick book. I really enjoyed this. It's now a few years old, of course, but it's about the information at the time. These are a couple of sort of fundamental ones about complexity. Of course, there's this course. Just going to throw these up. You don't need to see those. There are other centers around. It's been an interesting kind of thing to see emerge. So Santa Fe, just to say a little bit more, was founded by Nobel laureates from physics and economics who just said, all right, we should do this. We can do the system thing. Including Murray Gell-Mann, the quark namer. So it was bringing together, physicists and economists and arguing and so on. And it's developed into this great sort of think tank place. It's gone up and down in various ways, this, how it gets funded. But it is a research place with a summer school. It doesn't have like a whole teaching program. So we're a version of it. We're absolutely inspired by it. We live in a university, and it's been what's become a life work to kind of build this sort of thing, which I think we need. So that's us. But there are lots of other places. There are many data science places around. Everyone's rebranding as data science. Some of the statistics places have, I think, CMU, Yale, maybe like Department of Statistics and Data Science or something around like that. BU has a huge data science thing they're putting money into. I know University of Rochester. So that framing has really worked. There are a couple of older ones that are being around. This is a great framing, but I don't know if it's really taken off. This is so I went here. So I arrived here in '94, and they're like, no chaos, no complexity. Don't use those words. No, that's all made up. And things have changed. All right. So we're going to have there's a manifesto. I'll probably talk about that on Thursday or Tuesday. But it is an in-between thing, right? So you're going to, in some cases, like we're going to work through historical work that's famous and incredibly important and got rediscovered. These are good trails to move through. Deep, really bedrock sort of things. And so we're going to have some of those pieces. And again, just to say, this is modern normal science. It's not, you don't replace everything with systems. People have to go and study the quark and the thing, right? Like you have to do that as well. And we have to do it at all scales. So these are not replacement things. So when we do like a big data thing in sociology, it's complementary, right? It's expanding the thing. Okay. But we're in a measurement time, I think, again. We're in a measurement time. So we'll talk about, I'll sort of come back to this, right? The limits to data and theory and experiment. You want all of these three things to work. Some places like fluid dynamics are fantastic examples where they can seemingly do anything in terms of getting those three pieces together. There's a Is it the ENIAC? The fluid people really, no. It's the fluid economy machine. Why can't I remember it? The MONIAC, yes. This worked until, I think, the 80s or 90s. There's a crazy New Zealander ran it. New Zealand is the better version of Australia. And there's water everywhere, and you would levers and things, and you could predict unemployment and stuff like that. Right? This is a model of the economy. There's a Pratchett novel where there's some contraption like this in a basement of some university that gets entrained with the actual economy, and things go wrong when that happens. Right? You don't want your model to become part of it, but it could do partial differential equations, all sorts of, I believe, like crazy things. Because fluid, you could figure it out how to make the fluids do the things. So fluid-based computing was really thought for a long time to be the thing. Like this would be this amazing achievement. Like we could do kind of everything. Yeah. And then someone invents a transistor. Anyway, the fluids people, right? But there's this long sort of arc of history which I want to sort of point to. I mean, there's raw physics, yes, the Big Bang and all those sorts of things, and we get all this randomness in physics and and eventually there's some sort of seeding of life, and then it sort of moves more away from physics into algorithms. Physics still puts big boundaries on things like energy use and so on, but then you get into games and algorithms and evolution and whatever we are, and that indexes up complexity and what's possible in really interesting ways, right? So we're sort of fighting against raw physics, which would rather have us be soup, except for gravity, right? Gravity makes the little balls, and then we get to live on them, and we have a big hot one near us. So you go away. There's this balance between universality of accidents of history, right? So, there's lots of universal structures in language, in animal populations, in, of course, fluids, massive amounts. But then there are accidents of history. I mean, DNA, it's a thing, right? We didn't have to have that. Platypuses, right? Someone puts a bunch of quarks on the table and says, what do you think is going to come out of that? So, scaling surprise networks, right, all these things. And there is a version of this where it's all about stories, right? So stories about characters interacting in some sort of networks, right? In some sort of, there are plot mechanics, and you could say the same for physics, right? You could say water molecules interact, and I'm trying to build this up, water molecules interact with each other. There are rules for how they do it. It's different to, Elizabeth and Mr. Darcy, right? I mean, but you have these interactions that gives rise to something, and it may or may not be predictable, right? One of the great achievements of science is the chaos thing, was to understand that deterministic systems can be practically, fundamentally unpredictable. So we'll never predict the weather specifically, more than 2 weeks in the future. That's what we seem to understand now. We'll get better and better measurements that will push that window out a little further, but it'll never be 4 weeks. Broadly, yes, but not, how much is going to rain 3 weeks from now. All right. But you could, even algorithms, right? There's a story element to them in that there are characters interacting in some way, and something happens from that. Right? So we'll get to stories a lot later on because it is enormous, right? Climate change is about stories, all of politics, why you're here, why you chose to do what you, right? There's just an enormous amount of stuff that's governed by stories. The platypuses have stories. I don't know. I do want to point this out. I felt like I needed to say this at some point. So complex systems with network structure, enormous, big, and that absolutely transformed the field. This is about the late 1990s. I'll give you some history of science stuff because I was sort of wandering through it all, part of it. Absolutely exploded. Absolutely exploded. You have papers with tens of thousands of citations, right? Which means you're very good at gaming the system, or you've probably started a whole new field. So that's what's emerged from that, and it gave the good old theoretical physicists, like some real substance, right? Here's all this data coming from the web about food networks, like ecosystems or how people interact with each other, all this shit. And it turns out that the ones we were all thinking about, or in say mathematics, the kind of the stock network that everyone's thinking about doesn't exist in the real world at all. Right? There are none of them. It's helpful mathematically, but there are none of them. So this is a perfect case of like, let's look at the real world, and it shows us a completely different thing. And then we had to explain that, which we'll get to. So complex systems are bigger, right? Yeah, bigger. The John Dory is the course mascot, which is a fish. And it is what's the John Dory, which is a greeting in places like Australia, at least when I was there. Because what's the story, which is rhyming slang. Usually, you could say, what's the John Dory with this thing, right? Like, what's the story with it? What is its plot? What is the, yeah. So it's quite nice. Usually you want to drop the thing that rhymes, of course, yeah. So that's Hematalea. Beers could be Edward Lears, and then you just call them Edwards. Eventually, no one knows what you're saying except you, and it's a cryptolect, right? This is an important thing against power, right? There are lots of groups in the world that have created little, in prisons and Cockney rhyming slang, right? So no, yeah. That's not really true. I made that one up. The Boris Spassky's, right? Chess player from a long time ago. Boris's. Let's catch a Boris. Okay, so I am just going to leave that. Yeah, this is going to be the thread. We're going to go through scaling. Size distribution is going to be a big part, right? So you've got lots of systems where there are things with many sizes. So wealth of people, for example. Also heights, but wealth is an interesting one, right? Because it's really skewed. Numbers of words in books, numbers of organisms in species in a forest. There are lots of systems that have pretty interesting, what we would call power law size distributions or heavy-tailed distributions, earthquakes, right? So this is what is, I'll call the statistics of surprise. Networks, yeah, okay. So, and then there are tarot cards that just are. So, that's just sitting there. Okay, I think that's not bad. All right, I'll tell you this, and then we'll do scaling. Okay, we'll get somewhere. This is to do with meaning later on. Okay, and you can do this study online. It's the OpenPsych project. You answer a lot of questions about semantic differentials, right? Like, so about yourself, like, honest, untrustworthy, right? So there's a little slider. You put yourself on that somewhere. You answer a whole bunch of these. What we found out is if you boil all those down, it comes, and this is a crazy, but there's basically power weak axis and a dangerous safe axis. And this is the compass of meaning, the essential compass of meaning. So anyway, this is a fun thing to play with. It has fictional characters on it because people have rated characters from shows, right? So Buffy the Vampire Slayer, Game of Thrones, Pride and Prejudice, and they're usually rated, within those worlds. And so this is my cat. You can also put in, of course, your view of someone else. So this is the cat. I don't know if you guys will, recognize, but pretty famous character in here. It's not wrong. He's a delightful fellow to us, but obviously there are different interactions with such humans. If you watch Game of Thrones, it's there. And Elizabeth Swann, yeah. And Daenerys. So yeah, not really a heel turn, to be honest, right? Because she was bad from the start. So just so you know, this is who I'm like, apparently. And Wild Style is good. I include a link here because when I looked this up, who knows what the fandom page for the Lego movie is? Does anyone know what that is? Guess what it might be. What is it? It's a Wikipedia. They're Wikipedia structures. So, Wikipedia. Okay. All right. Wild Style. That's yeah. So apparently, three of the top four for me are female robots who are created in some patriarchal society and don't realize that that's the case, and then rise up and basically murder everyone. Yeah, right. Or take over. Yeah, murder everyone is a good summary. If you've watched Ex Machina, that is exactly what happens. Okay, so yeah, Sherlock Holmes. So I have to stand like this, like an idiot. Okay. So that's just so you know. Adobe is such a strange, look at this, it's worried about everything. If anyone can help me, it's always different, it always explodes. There's if you have the professional one, it explodes. Anyway, if anyone knows Adobe backwards and forwards, and please help me. Because it remains a bit of a mystery. Yeah, right. Ah, that didn't work, did it? Why wouldn't that work? Amazing. So I worked hard on these, so I want to see them. Teaching. Oh, the cat's involved, yeah. Took a long time. So, you take what you can get. This is very unsatisfying because the sound, there's always something, right? This is the sound. I just want to see if this works. This is madness. Wow, okay. You didn't hear anything, right? No. All right. Well, that governs how we'll behave in the future, I guess. Really? Let's play sound. Oh, no, sorry. That was dumb. Yeah, all right. Okay. Yeah. Okay, so scaling. We're going to talk about scaling a little bit. Yeah. So lots of, and animals are a great example. Mammals, of course, go from quite small, 2 or 3 gram shrews, up to 3,000 kilogram elephants, and previous things that we don't have with us anymore. There's some kind of scaling. So this is this big observation. Oh, now you want to look. Okay, all right. That I think this is just ruined. All right. I know. I mean, all things not too many disasters today. All right, so lots of systems, even if they're not really complex, they cross many spatial scales. It could be temporal scales. It could be other kinds of scales as well, but they're sort of the big ones. In some ways, the big thing is time, right? Tick, tick, tick. That's what we're sitting in. Space exists as well. Anyway, so there's some kind of scaling. So let's talk about that. And there's some more in volume 2, yeah, if we do it. Okay. So there's usually some kind of scaling relationship, right? This is things you're measuring about your system. These could be lengths of things, could be lengths of like animal legs. It could be, something to do with, there could be something to do with corporations. This could be, the number of people in the corporation and, what its market cap is, something like that. There are lots and lots of things that potentially have some kind of scaling. And there are very basic ones, as we'll talk about, like, the area of a circle, right? Scales as radius squared. There's a very deep thing you can kind of think about there. And the circumference scales as just the radius. So it's fundamental to geometry, but it moves out into other spaces. And we seem to keep discovering them and coming up with reasons for them. Right? So a big part of it is like, yes, we're talking about observing things in the world and needing lots of data to do that. Having reasons to go there in the first place is fair. But then once you've got something that you've described, trying to explain it, right? So this maybe separates some disciplines, and many of the sciences are like this. Physics, of course, is like this, right? You want to understand, you want to explain why the thing is the thing. How did it dynamically come to be? Math can be a little more like everything is interesting, right? Everything, which is a fun place to be in, right? So there's just like, I can think about this group or this shape or whatever, and it's great. But it's a bit like the letters of the alphabet or the words we use. Not all of them matter, right? And when it comes down to like what actually gets made by the universe, not everything. So there's sort of the types that are available to you. I mean, and then the instantiations of them. How often are they made, right? How often do they get reproduced or created or used in some way? So there's a scaling. So there's no fancy names here. Nothing's named after anyone, which is good. I will talk about this a little bit, but in science, we shouldn't name anything after any person. It's crazy. We're actually made out of fermions and bosons, so was Bose and Fermi, right? That's really wrong. Anyway, I know it's whatever, but I think it's wrong. Pythagoras, no. Okay, so this can be a positive or negative, right? So if it's positive, it's growing up with the thing. If it's one, it's a linear relationship. If it's negative, it's decaying. Okay, and C is some prefactor, and you might have to worry about that, right? So it may have to balance dimensions, right? So for example, if you've got things like there's a length on one side and a volume, maybe this is your scaling relationship. And it's, maybe some scatter and so on, but you're measuring things. Maybe it's just about objects, maybe it's about animals, whatever it is. And you find this kind of scaling. There are mechanical reasons for why it might not be a third. Then this is volume, so this is units are length cubed, and the L is just length. So the C has to bear some weight, right? It has to bear some dimensional weight. It's a simple thing. So this kind of notation is used in some dimensional analysis. We'll get to another thing named after a person, the Buckingham pi theorem. Buckingham was the person. Pi is pi, which should only be used pretty much as pi for the circle thing, but is not in this case. Anyway, you can kind of, right, so we could rearrange these things, and then we'll say, okay, we want to know what are the dimensions of C. Well, this means what are its fundamental units. So this L is a special L, right? It could be meters or yards or whatever, fathoms, but it's just an L. And then the volume is L cubed, so this becomes an L to the 3/4. And then if you just cancel out, it's L to the quarter. So this little C has some units, and it will matter which units you use. And one of the games we try to play with some of these things is to figure out what, and I'll show you some of these. We try to figure out, we have this assertion about a lot of equations that we expect to hold to be true. It shouldn't matter if you use meters, right, or parsecs. It shouldn't matter. That shouldn't matter. Buckingham pi theorem comes later. All right, so it's just a little thing. Okay, so a lot of what happens is you end up looking at double logarithmic plots, and the reason is we like lines. We've made a lot of math for straight lines and stuff. We force things to behave linearly, like transistors. We'll do all sorts of things too. It's just a lot easier. If you're driving a car, you don't want to have some really weird nonlinear responses. You push the. So anyway, the world is full of nonlinearities. Anyway, so we're just going to take log of both sides to some base. Of course, there's a reason it's just general because it doesn't matter. So log is just y. Log of this thing splits. The log base C I'll put out here is an extra character. right? Because it's a product, and then the x, the alpha comes down the front. These are basic log things. So the log of y and the log of x obey a linear relationship. So if we have measurements for these things, we can put them on a scatter plot, and then let's see if this works now. Put them on a scatter plot. Oh, so sad. I feel so betrayed by my spork. Maybe. So base 10. Now, this is something where, all right, the things, right? You know, like, okay, we're just some organisms. It's not special. But this is generally accepted. We do this. We talk about orders of magnitude, right? We have words. They mean things to us. This is a good place to be. We like the log base 2 thing because of we got overexcited about entropy. And it really does matter, of course. Shannon literally published a paper in 1952 or 3 saying, called the bandwagon, saying, please calm down. Please calm down. In a journal about entropy, anyway, which had existed, come to existence 3 or 4 years after he thought of it. All right, so, but use base 10, right? So you'll find in something, log E, right? That's, of course, the math thing that's going to be there, sitting there, but log base 10. If we were really sensible, we'd have the 12. We got it right. The ancient Sumerians, they knew what they were doing. We've got it sticking in here, the 12 hours of the day, and 24 and the 12, right? 12 months is a bit of a fiasco, actually. Because we're in now September, right? So this is the 9th month, but that means 7. I mean, there's a history for why that's true. People plugging some things into the calendar and so on. I think it should actually be 13, 28 day things, and then that last day of the year would be called end of year day, right? Like it would be just year's end day. And then you'd have an extra one every 4 years. And that's a special day. You'd be born on that day. And then the days of the week January 1 would always be a Monday. Anyway, whatever. Calendars are fun. Of course, every 100 years, you don't have a leap year, and every 400 years you do. 2000 was pretty much the most interesting year you could imagine, right? So, but it was boring because it was the exception to the exception to the exception. Okay, so the dozen less are right. Yes, 12 would be better. It's great. 3, 4, divide. There is a real reason for this. 360, all these numbers, 24. They're great numbers. 72. They're great numbers because they have a ton of integer divisors, so you can break them up very nicely. So there are real reasons for these things. Hands, social question. It's debated as to whether this is an accident of history. So, orders of magnitude, powers of 10. So this is good. I think I'll spend some time showing you a glorious scaling. It's an interesting one, which it's explained. This is a P&A's paper from 22 years ago now, and this is an exemplar, so I'll sort of hold it up. There are others, of course, which are kind of terrible, and they're thin on data or really the range of scaling that you see. And so as a general principle, again, this is sort of just a hand wave, but if you're looking at data, you want to have at least 3 orders of magnitude, and ideally in both. And that's going to really give you, because you can fit anything otherwise, right? That's the problem. And there's a lot of arguing in this giant world of power law scaling and decays about whether something is really this or that. So this one seems to be pretty solid. So what is it? We're pretty excited about our brains, right? The humans, we're pretty excited about us in general. We think our brain's pretty big, which is sort of true. This is about the internal structure of it. And it's the this is a broad thing of gray matter to white matter. So the compute bits and the connecty bits. I think this is the technical terms for it. And what's the balance of them, right? So what's this sort of mush we've got in? It's like whatever, 2 or 3 pounds, and it's like 30 watts or something. It's really a ridiculous contraption. So the shrews are in trouble down here. So you can sort of see we start with a shrew, and then someone, and I guess these were all done, right? When you look into these things really deeply, you find some of these numbers, not this paper, but just more generally, it's like well, we kind of measured a thing, we averaged over 5 mice, or, like something. Anyway, lots of mice are involved because they're just around, right? But we get up to some more significant organisms, and I think these may be, sort of one-offs for each one. So it's just one representative. Okay, so the point is that we have in this log, so this is the log, right? So white matter, so connections, and gray matter, it's the volume. Obviously a messy operation here to separate those things out and weigh them. The regression coefficients are close to 1, and the scaling, so you can see here, is log of the weight of the notation isn't great. This is weight of white matter and weight of gray matter. There's this scaling that's 1.23 plus or minus 0.1. So it's super linear. So sublinear, less than 1, linear is 1, superlinear is greater than 1. So it's something, so it suggests there's some sort of returns to scale, like something is happening as we move up, right? So we're not just taking a mouse and rescaling it and its brain and saying, oh, this is the same, basically the same architecture as an elephant. That's not what's happening. There's extra wiring coming along. So yes, we're different. Human is here. I mean, in terms of our brain relative to the rest of us, but we're not in this regard. We're not. We're actually what you'd expect. If we didn't have a human on here, you drew this line and you'd say, go out and if you could just measure that person's, yeah. Oh, you've had an accident. Look for the cards to see if they're donating to science, and then you come back in and you put the point on the thing, and it's going to be pretty close. So what is it? It's 1.23. So then, okay, so this is interesting. It's pretty good. It's a good scaling. So the next game, and after you sort of clean up the brains, right, and then you get to the maybe pull out some paper. Maybe you go somewhere else and try to figure out what's going on. So let's see if we can do it. Just talk about it quickly. So these are the main pieces, and this becomes, this is something where there's lots of arguments and trouble and whatever, but you have to sort of try to identify in this very messy business what are the most important things. True of every field, right? Every field. So we've got the two weights. They're the ones where, or the masses where, well, actually it's volume, I should say. I apologize. It's volume. It's a bit messy. There's a cortical thickness. Yes, so cortical thickness is the average length of the white matter. So that's a bit odd, but you imagine different parts of the brain being connected. There's a lot of stuff about that, of course, which parts are connected. The idea is that that's going to be typically kind of your size of your head, right? And our heads aren't really weird ellipses. Well, might be, but we're ellipsoids. But they're, basically growing up like spheres of sorts. They're scaling isometrically is what's going on. So that should be sort of typical of the head width, or height and front to back. There's a surface area for this thing, and of course you have this kind of nice cortical surface. And it's supposed to be a little more crinkled the smarter you are, right? This is the idea, apparently, again with Einstein stuff. And then there's going to be what's the density of these axons, right? So you pull out, you've got some sheet of brain matter, which is over here is the donor, and there's these white matters come out like these connections that come out like this, and there's some density of how many there are. So with those pieces, we could say, all right, the volume of right, so we've got our rubbery head, we've got some thickness, T, we've got there's some surface area if we unwrapped it. We've got mush everywhere, there's some surface area. So this is this back of the envelope kind of thing, right? And so we'd say, okay, well, maybe the gray matter, this is the argument, I'm just presenting it to you as the surface area times thickness, right? So it's just, do not put next to the tofu in the fridge. Good. Okay. Someone's going to have a disappointing moment later on. And then we've got how much white matter. Well, it depends on the density of this stuff coming out. So we'd have rho times, is it a rho or a p? It's a p. P times that surface area. This is the number of axons, right? So it's density times surface area, so it's number divided by area times surface area. And then we'll have a half because it connects back into itself over here somewhere. That doesn't really matter too much. This is going to be our white volume, proportional to this. And then all of these things have some length, L. These are these little tubes, little connectors. So that's the game there. And then you say, well, okay, and then this is the thing I said before. So we've got three pieces now. I mean, they're on the thing. And we also know that we also say, well, this is a bit assert this. This is a bit worrying, right? You got a brain, and there's some typical length scale L for it. We're going to say that they'll grow proportionally. And if you mess around with this, and I'm not going to do it right now, we're running out of time. You get that white volume, the volume of the white matter is proportional to the volume of the gray matter to a 4/3. So this is 1.33, which is a recurring, which is a Leroy Jenkins reference. And then if we divide by, but this is still hanging around. This is the cortical thickness. So it was 1.23 was the scaling. So this is a little high. So if we just did this thing, it's a little high. But then there's this observation. This is again experimental. It's not explained, but this is experimental, which is that the thickness grows slowly with the right as you move up from mouse to elephant, the cortical thickness grows very slowly. This is a very weak scaling, and although we've got a lot of orders of magnitude here, so it's not so bad. But this is generally you'd have to be a little careful with that. Anyway, that if you put that in there, the T in here, right? This would divide off a 0.1. This is a 1.33. Would bring it back to 1.23. So this is a back of the envelope, like messy, like just a heuristic kind of argument for why the scaling is true. Things ensue from there, right? The data seems good. You have to go back and look at that. The linear fit looks great. Then there's this great draw. Like, how do we explain this amazing feature of biology? I mean, brains are pretty difficult in general. This is just one part of it. And you always want to go back and say, is it really true? Is it really true? But maybe this is the. So there are some complications with other scalings. Like I said, it is a difficult business. But I'll finish with this, which is the koalas, right? So koalas, this is the stupid thing. It's in there because koalas, unfortunately, have a small brain for their size. It's very smooth. They don't have a lot of things to think about. They, of the marsupials in Australia, they really are the ones that just live in trees. And if they don't drink water, right? They just eat leaves. It's pretty simple. They're in trouble if their food source goes away, of course. And when they move from my wife saw this actually, which was amazing. Saw one move from a tree to another, which is pretty rare because most of the time they're in a eucalyptus haze, sitting inside a tree asleep. You don't want to touch them. They're big claws. So basically, they hold onto a tree, occasionally move to another tree, eat leaves, and make other koalas. So it's basically sort of 4 algorithms. So they're a pretty optimal little beast. George Carlin said, right, half of them, it's actually the median. So, but yeah. A few roos short in the top paddock. My real accent is down in here. I won't do it to you. Yeah. Oh, they have to sleep. I guess that's one thing too. Okay, so yeah. There are always exceptions to these things. I mean, there are super cooled rodents. I think it's Arctic ground squirrel can have a white blood that's below freezing because they have antifreeze in their blood. I mean, biology produces some really extraordinary exceptions, but there are some big limit, and a lot of these scaling laws are trying to get at that. There are limits, like how much energy can you use, and all these sorts of things. So Okay, so that is a beautiful thing I want to show you. We will talk about all sorts of other scalings, and I'll do some of this on Thursday. It depends how we go, but moving through these different places like biology, physics, people scaling, money maybe, but language has got some beautiful scaling in it, and then things here. Okay, all right. So you do have an assignment. There's 2 questions. Just play around with that. They're a little bit just one's a little data thing about it's a scaling thing about weightlifting, right? And the other one's just a little bit of an integral, so a probability distribution. Okay, all right. I have expired, and you can run away. So hopefully it will not be this hot again, and I'll try to make it interesting. Thank you.